Hello, I hope you're doing well. My name is Mahmoud Kiasuri and welcome to the new chapter of electrical circuit. So at this point, we are going to talk a little bit more about the capacitor. As you guys remember, we mentioned very briefly about what is capacitor, what it's going to do, what are the related formulas to that. But at this point, we are going to talk about it in detail and see that what would happen if we combine them together. What would happen if we do have the series combination? What would happen if we do have a parallel or maybe do have the mixed combination of all of them, and how it's going to affect our whole system. So without further ado, let's talk about it. So as you guys remember, the capacitor was a component that it has two important parts. The very first important part was about the plate or the top plate. We call it as a connector plate, that it has the area, and another plate that we call it as a secondary one. So by having these two and connected directly to our voltage source, it could be a normal DC voltage source, it also could be AC. It means that it is just connected to one specific component that it's going to activate the electrons inside these two plates. And by having the activation of electrons, we do have the movement from one plate to another. By having this movement, my plate is going to be distinguished into two parts, the positive part and the negative part. The field between the positive and negative, which is something that we call as electrical field, is a place that my capacitor can store the energy inside of that. So how we can see that how much energy is just stored by using different kind of formulas. The very first formula that we knew was about the C equals to Q divided by V. So what was each of them? C was about the capacitance of the capacitor, we just showed with Farad. The Q was amount of charge, or we call it as Coulomb, which is related to how much electrons actually we do have inside this field. And finally, V is related to voltage, how much is the voltage of that specific capacitor is at each time. We also learned a couple of formula related to that, but at this point, we are not going to talk about it that much. So a capacitor is going to store electrical energy in an electrical field between the two conductors separated by a dielectric. This dielectric could be air, could be mica, could be anything. So it is an in-string property defined by the geometry independent of the current charge. So as you guys know, it is something related to the geometry of our capacitor, which we know it as capacitance. Another important thing that you have to know is that typically capacitors are going to be told as microfarad, nanofarad, or picofarad because 1 farad is so high. That's why most of the time we are using these. So let's look at the geometry itself. When you look at geometry, as you guys know, we do have two areas. We do have the area number 1, which is another which is going to could be the positive plate, and the area number 2, which is going to be what? The secondary plate. And when we are talking about the area, we are talking about the length of this specific plates, but length of common space. As you can see over here, both of them share a common area itself. So we do have the specific formula in order to find the amount of energy, or U, is actually stored inside my capacitor itself. That U equals to half of C times V to the power 2. So U means that how much energy I do have inside of it. C is the amount of capacitance, and V to the power 2 is just the voltage itself. So energy is going to store in the joules itself. So one thing that you guys have to know is about the formula related to capacitor. We mentioned it last time, let's just mention it again. C is equals to epsilon A divided by D. Epsilon is related to your dielectric, related to permeability. The better dielectric you have, the better capacitance you would say. So they have the epsilon and C, they do have the direct relationship. Then we do have the common area, the area between those two places. The more area you have some kind of the more capacitance you would say. And D is the distance between, or the separation part between those capacitor. If you increase it, you are going to decrease your capacitance and vice versa. So the role of capacitor is circuit design. Why we are going to use that? As you guys just know, we are going to use the capacitor in order to store energy. Why we are going to store the energy? Because in the future we are going to use it for another purpose, that a capacitor is going to act as a source itself. In the future and future parts, in most probably in advanced electrical circuit, you would see that why actually we use the capacitor. The capacitor, rather than just being a good source, has also other kind of benefits. It is going to help you in order to smooth out your output signal, which right now we don't know anything about it. That is totally fine. But capacitor, alongside with that inductor, they do have very important electrical and electronic usages. So at this point, we do have the voltage distribution. Obviously, capacitor like the resistor or maybe the future inductor, they're also going to have stored amount of voltage, but this voltage is not going to be constant all the time. This voltage would change based on the time. So this guy is going to influencing the potential drop across the network based on the timing itself. Again, it's not like the resistor that when you have, for instance, the voltage of resistor is 5 volts, it's going to stay 5 volts all the time. But the voltage of capacitor is going to follow a formula, the V0 times 1 subtracted by negative t divided by RC, as you guys know about that. It means that at the beginning of the point, you do have a very low amount of voltage, but by increasing that, your VC is going to be as the same as V0 itself. So as I just mentioned, capacitor is a charging device. It means that it's going to store the energy like the container that can store the water. It can store the energy by using the electrons or coulombs or electric field inside of itself, and later we can use it. Another thing that we have to know is the voltage or the current of capacitor is not following a constant formula. It's going to consider a transient behavior and is going to managing the time and flow of changes. So it is very important to know that. We talked about the normal capacitor and what would happen if you do have a one capacitor and one resistors in series. So what would happen if you do have the combination of capacitors? It means that I do have C1, C2, and C3 in series. We do have it as a single path. So these connections, as we all know, based on the resistance, are end-to-end, sharing one exclusive charge path. What was the charge? It was Q. Q or charge is going to play a role of current in normal resistance. At this point, we don't know anything about the current. The only thing that we know is about the Q, is about the capacitor of each of those, the capacitance of each of the capacitors, and also about the voltages that each of them is going to store. So based on that, let's talk those some kind of terms again. When I do have a path of capacitor that all of them are connected in series, I know at the end of the day the amount of charge that each of those capacitors are going to have are going to be the same. It somehow means that I do have what? I do have this current that is going to be the same for all of them if I'm going to talk about the resistance. Q is acting as current in resistance in capacitor. So at the end of the day, when everything is settled, when all of my capacitors are getting charged, the Q total or amount of each Q or some kind of the coulombs or energy, the coulombs inside each capacitor would be the same. On another hand, we do have the voltages which is going to follow the same path as resistance. It means that at the end of the day, the total voltage is going to be V1 plus V2 plus whatever capacitor that you have if all of them are in series. And finally, important thing we have to know that the C equal, which obviously we do have the C equal, right? We have the R equal, we do have the C equal, is going to be smaller than your smallest capacitor itself. Why is that happening? Because your C equal is going to follow this formula. This formula is very familiar because, as you guys remember, we had this formula for resistances when all of them were in parallel. But at this point, we do have the vice versa condition. It means that my C equal is going to be something like this. Obviously, you can prove it very easily, but I don't want to waste time on that one. And also, we know that when we do have two resistors in parallel, it is going to follow the same formula that when we do have two capacitors in series itself. It means that the C equal is C1 times C2 divided by C1 plus C2. So let's see an example. Imagine that I do have the condition that my source is 12 volts and this 12 volt is connected to 6 microfarad and another one 3 microfarad. So the question asks a couple of things. The very first one is about the C equivalent. As we all know, the C equivalent, we can use this formula 1 over CEQ equals 1 over C1 plus 1 over C2, or we can use the C1 times C2 divided by C1 plus C2. The same formula that we used over here for this section. So we do have 6 times 3 divided by 6 plus 3. At the end of the day, we are going to have the microfarad again. Be careful about the prefixes. Then we do have the total charge. As I just told you, at the end of the day, the total charge of the Q, we can just Q equals to Q1 equals to Q2. So what was the formula that we have? As you guys remember, the C equals Q divided by V. You can just put it inside the triangle. It's somehow like the Ohm's law, but it's a little bit different. Because if you remember, for the Ohm's law that we had what? That we had R equals V divided by I. But at this point, we do have C equals Q divided by V. C is the capacitance, R was the resistance. The Q was the charge, and I was the current, and voltage is just the voltage itself. So the only common thing is voltage. But rather than that, everything would be different. So the Q equal obviously equals to C equals times the voltage that you have, or the voltage of the source. So you have 2 microfarads times 12 volt, and you do have 24 microcoulomb. As you guys know, they are 4 units. For the unit measurement for Q is coulomb. And finally, it asks for the V1. As we all know, V1 and V2, if you add them up, it should be the same as our voltage source. So V1, again, we can use this formula, is Q1 divided by C1, because I know the Q1, Q2, and the Q equals the same, so we don't have to worry about it. And if you do that one, your V1 would be 4 volt and your V2 would be 8 volt. And it makes sense because if you add 4 and 8, you do have 12 itself. So what would happen if we do have another configuration, the parallel configuration? It means that we do have the shared potential. As you guys know, whenever we do have the parallel components connected each other side by side, it means that they do have 2 common connections, right? So the very first thing that we know is just the same as resistors, that the V equals V1 equals V2 equals V3. Based on the resistors, you guys know that whenever we are talking about the current, I equals to I1 plus I2 plus I3. We do have the same scenario over here. It means that my Q, or the Q equal, is going to be equals to Q1 plus Q2 plus Q3, but we do have another story about C. So let's look at it this way. So V total is going to be what? V1 equals to V2. Just the same scenario that we do have about the resistance. Imagine that you do have 2 water containers, that both of them are connected to some kind of source, to your faucet, and whenever you open that, at the end of the day, the height or the amount of water inside each container would be the same. On another story, imagine that you're talking about the amount of water you're going to inject into 2 containers. At the end of the day, your Q total, or amount of total that you have in water, is going to be Q1 plus Q2 plus whatever branch that you have is connected to parallel. And finally, this is very important, the C equal is going to be bigger than the largest one. The same thing is happening for parallel capacitors that happens for the resistors itself. It means that your C equal is going to be C1 plus C2 plus C3 itself. Again, you can prove it by using the formula C equals to Q over V, but just memorize it. So this is something that you guys have to know. The parallel combination of capacitors is the same as the series combination of resistors. On another hand, the parallel combination of resistors is the same as the series connection of capacitor. Formula-wise, unit measurement-wise, it would be obviously different, but be careful about that one. So let's have a condition that my 10 volts, the DC voltage, is connected to 4 microfarad and 6 microfarad. So at the end of the day, the main question is that what is the C equal? As you guys know, this parallel combination of capacitors is going to be 4 plus 6 or C1 plus C2. So we do have 10 microfarad. Then about the Q, or about the amount of coulomb or amount of electrons for each of those branches. So we know that the voltage of this guy is 10 volts and the voltage of this guy is also 10 volt. I do have the C, I do have the V, I can find the Q. For each one, as we all know, the Q equals to CV. The V is 10 volts and QC for the first one is 4 microfarad. For the second one is going to be 6 microfarad. So what do I have? I do have 4 microcoulomb for the first one, and I do have 60 microcoulomb for the second one. If we add them up, you do have your total Q. So what would happen if you do have the combination of that? Obviously, not all of those questions are going to be simple as series and parallel. We do have this maze, we do have this connection that could be a little bit confusing at the very beginning of the point. So before just talking about the questions, let's talk about the algorithm that we can use in order to simplify all of the circuits that you have around yourself. This algorithm easily would say that the very first thing you have to do related to your capacitor or the combination of capacitors is that you have to redraw the circuit based on the knowledge that whenever you have the connections end to end, it means that all of them are series. Whenever you have the connection in parallel, or it means that when two of them are connected to each other, you do have it as parallel. Just I'm going to try to clarify it by yourself. Try to redraw it. Then we do have the reduce the parallel. At the very beginning of the point, try to reduce any kind of parallel combination that you have. As you guys know, the parallel is the easiest part because the only thing you have to do is just add them up. Then reduce the series one. It means that at the end of the day, you have to find all of your series, try to find that. Sometimes this formula is going to be a little bit challenging because not all the time you do only have 2 capacitors. Maybe you have 3, maybe you have 4. It could be a little bit challenging. Then try to do the hard work and reduce the series one. And after that, another step is going to be about repeating the factor. Try to continue this until one equivalent component remains. It means that you're only going to have one C. Then you obviously have to reverse. Work backward to distribute Q and V because the C equal is not going to be end of the question. Probably it's going to ask to find the Q and V for each of them. So let's see a very simple example. Imagine that I do have my 12 volts. It is connecting in series with 3 microfarad, that 4 microfarad and 2 microfarad are in parallel. As I just mentioned, try to redraw it. We don't have to redraw that one because it is very clear. So let's try to work with the simple part. The simple part means the combination of the parallel capacitors. If you have the 4 and 2, at the end of the day, you do have 6 microfarad. Then we can work on what? Then we can work on the series one. 6 and 3 means that you should use the formula either 1 over C1 plus 1 over C2 or 3 times 6 divided by 3 plus 6. So you can find it as 2 microfarad. Then you can find anything. For instance, at this question, it just simply asks to find the amount of total system charge. This is Q is C times V, and simple as that. So the symmetry of the circuit loss, this is something we talked about it at this point. Again, this lecture wasn't that kind of challenging. The only thing I tried to focus on was the continuous part of the previous session that I talked about the capacitor. I just tried to refresh your mind. What is the capacitor? How it's going to store the energy inside of itself? And what would happen then if we combine more capacitors? If we do have the series combination, if you have the parallel combination, what would happen to them? And you guys have to remember, whenever we are talking about this condition, means that your capacitor are already charged. It means that we pass through the transient one. Because maybe some of you would ask right now, you mentioned that the voltage of capacitor is not going to be constant all the time, and it depends on the timing factor, which obviously right and related to the thing that we have for the previous chapter. But right now, we just assume that if it's time passed after the 5 tau, 10 tau, whatever time passed, and everything is charged, we pass the transient timing and we just reach the stable condition. On that point, we can say that these numbers are right. The voltage of capacitor are going to stay constant, the Q is going to stay constant, and you can find anything you need. Again, if you have any question, don't forget to put a comment down below. We'd be more than happy to answer that. Probably I'm going to have another chapter related to this part in order to solve the other kind of question related to the voltage and current, of what would happen if we are talking about the transient time, if we are talking about the between of these two times. So what would happen on that condition? We are going to talk about that, no worries. And I'm making sure that all of you understand everything related to capacitor. We are going to move into the inductor itself, and we are not going to forget that probably 99% we are going to have a lab related to that, because on that point I would like you guys to see that what is actually happening. That is so fun. If you like this video, I would be more than happy if you just like and share it with other friends. My name is Mahmoud Kiasari. Have yourself a great day, night, whatever. See you around.